the next presentation. It will be lighter, let's say, than the previous one. So we will give you some practical directions for the efficient development of sensor-based groundwater monitoring networks. So Andreas, you could start. I cannot hear you indeed.
The mic is off.
Okay, now it's on. I can hear you. Now I cannot hear you.
Now you can hear me, okay?
Yes. Okay.
You turn on your microphone, please, Vasilis. Okay, so we're going to see into practical directions for clearly identifying the monitoring needs, finding the appropriate groundwater wells, and making the technically optimal and budget-wise choice for sensors. Let's move to the next one, Vasilis. Thanks. So, on the first aspect, clearly identify the monitoring targets. We've said this many times. What you need to monitor, where and how often. What, where, how often. For groundwater salinization studies, the what refers to groundwater salinization processes depending on the source. And this is very important. You go differently depending on the source of salinization. Where to monitor? Spatial distribution of groundwater salinization. You need to capture this somehow. And of course, how often? The how often question refers to the time response of the system in groundwater salinization processes. If you have a very responsive aquifer, you don't need, you need very high frequency. If your aquifer is inert and the response time is very low, or you don't expect any dramatic changes, you don't need to go for very high frequency. Let's go to the next one, please. Right. Second aspect, find the appropriate groundwater wells. The ideal groundwater monitoring wells clearly respond to what and where factors of monitoring targets. Technical points that have to be addressed in selecting the wells to perform your monitoring. Dedicated research wells are not available in many cases, and therefore, what you have to do is to find easy access down the hall and enough space in the wells you are selecting. This is the case in many Mediterranean countries. You don't have any dedicated monitoring wells. Some people are very lucky to have fantastic research areas with dedicated monitoring wells. Unfortunately, this is not a typical case. So, most of the cases you have an abandoned well or an abstraction well where you have to make sure that you put your sensors in. And to do this, you need to find out exactly what the specifications of the abstraction well is, so that you can host your sensors in a safe way. Then you need to find an easy to approach and safe well from theft and damage. And this theft and damage could be a result of vandalism, but could also be a result of too much vibration of the pumping system in case you decide to install your sensors in the abstraction well, with or without a housing pipe. In both cases, damage and theft is an issue, and you have to make sure that you take all possible precautions to resolve the possibilities. Well constructed and in good condition wells. You don't go for wells that are dubious if they are operating hydraulically and if they give you direct access to the flow system. You don't go for wells that are ready to collapse, because you are going to have a problem of losing the instrument and also losing the data. Access to the groundwater well, at least for the time period required from the project. You start a monitoring project, and you need to make sure that at least during the period this monitoring network will operate, you have frequent access to the wells so that you can service the sensors, download the data, or do whatever works that need to be done, maintenance, calibration, and so forth. Last but not least, you need to make sure that the wells you are going to select belong to an owner with whom you have very good collaboration. This is of utmost essence. Don't want to install the sensor in a private property and then come back after 2 or 3 months and find that the sensor is dumped or the cable is cut and the sensor is down in the saturated zone. You can't have access to it or damaged or whatever. You need to have very good cooperation with the well owner. Next one, please. The aspect 3, which is next.
The next one I think is mine. Yes. So let's give questions and answer them one by one now. So we have to decide if we would like to have a low profile installation or not. And with the term low profile installation, we mean the installation that is not easily visible from the surroundings of the monitoring point. Nothing is perfect in this life and there are always pros and cons. So with the low profile installation, we have lower chances for our sensors to be stolen, damaged, or have some disruption of the installation point. But we have restricted options related to the energy source that we use and the telemetry. Extra crucial, we have to consider the energy source. So the options that we have are for external energy source, which is usually rechargeable, since for most times it is a battery attached to a solar panel. The second option is the internal battery that can be replaced. The third option is the internal battery that cannot be replaced, and this is a very common trend in the modern sensors. And finally, we have the external battery packs that can be used in the case that the battery of the sensor is drained, but it cannot be replaced. So let's discuss on this critical question: internal battery or external energy source. For sure, more preferable is to have a system powered by an external source. But the internal battery is usually the only option for low profile installations. And you have to pay attention to the fact that not all the sensors have all the options. Okay. For the most cases, okay, you can have both options, but this is not the case for all the available systems out in the market. So let's have some hints regarding this big question. Battery duration may vary significantly than this reported by the probe manufacturer. From our experience, if you reach, let's say, up to 70 to 80% of the expected battery life, you must be happy, since the reported one corresponds to ideal conditions, which are definitely not feasible in the field. Very critical hint. Internal batteries are several times, as I said before, not replaceable. So you have to give a very special attention to the monitoring frequency. For example, for this sensor, you have a maximum, which is the theoretical one, of 200,000 readings. You have to spend those readings very wisely. Another hint, most probes are giving the battery voltage as an output, and some probes can also provide information about the energy consumption. It is here's an example that I give you that we have the rest capacity, the capacity of the battery that remains, and also we have the power in micro ampere hours. Okay, so it is very wise if you have a telemetry system, to assign a relevant alarm in order to avoid losing your data. So, another hint. For large, let's say, systems, here you can see one monitoring station that we have in Pineos Hydrologic Observatory. You have to ensure that you have large enough solar panels or wind turbines to sufficiently charge your batteries. We spend more than 1,500 euros in order to finally achieve, after 6 months, sufficient energy for this complex station, which includes a wide range of sensors, one meteorological station, a cosmic ray neutron probe, a snow depth sensors, etc., etc. You can also see that we have wind turbines, we have huge batteries. Okay, so for several months, we had to adjust this setup and interestingly, finally conclude that a classical battery with this, which can support this start-stop system that the modern cars have, is the best option. And after having paid several hundred of euros for some special bubble batteries, etc. And also, you have to avoid the shading in the solar panels. I don't know. I know that it is very, very simple, but it happens. Andreas, please.
So, in terms of telemetry, telemetry is a good option. It is an essential option. And you can have a non-low profile like this, where the sensor lays into the well and you have a telemetry unit into this box, driven in energy terms by solar power. Solar panel. This is one of the options, as I said, the outside of the well telemetry system, which is not low profile. But normally it's cheaper because the equipment is bigger, and the bigger the equipment is, the lower the price is. Then you have an onboard telemetry system which goes in the well, and this means that the sensor and the telemetry unit are fixed on the same cable, connected with the same cable, and they go hand by hand. You don't have an option to remove the telemetry unit and go on a standalone. It's a fixed system with the batteries and the telemetry in. The good thing about it is that provided you have the right well, you can install it in the well and nothing is visible. Same goes for this system, the outside the well telemetry system, where the great difference is that you can either install it again in the well with the right configuration and not have anything visible, or you can install the sensor in the well and the telemetry system outside the well in a pillar or in the shack of the well, if such a thing exists. So these are the three main conditions, and another difference in the outside the well telemetry system is that, of course, you can have the sensor stand alone with its own energy, or you can have it with the energy, with the telemetry unit that drives with energy the sensor as well. And the next one, please, Vasilis. Okay. The big question, install telemetry or not? Telemetric data transmission is a very good option if you can afford it. and if the chances are there. It's more advantageous from all the perspectives, but it comes at a cost. And this cost is twofold. One is the capital expense, because the telemetry system prices range between 800 euros and 2,500 euros, depending on what you select and what it can do. And also you have an operational cost, which again can vary significantly from a few euros to lots of euros. Next one, Vasilis. Right. So if you go for GSM connection for telemetry, then you need to check if you have a strong enough signal in your area. Because you may buy the modems, install the SIM cards, and not be able to operate simply because you don't have any strong signal there. Next one, Vasilis. Okay, now, hints. Again, useful hints. There are options for installing the telemetry and on a low profile or not so low profile, as you can see here. The first one is obviously low profile. This is the antenna actually. And the other one is obviously a non-low profile configuration with the pros and the cons Vasilis and myself explained before. If we go to the next one, please. Right. You need to define and make up your mind whether you want to consider new data transmission technologies instead of 4G or 3G or 2G. And these alternatives are the LoRa protocol or the XB protocol. And this can be very, very easily used if we're talking about a big network, when you have many, many sensors that can be connected to a central unit, and therefore you only need one SIM card to try to relay the data to your cloud. This is very, very useful. To decide on this, you need to do an analysis of the capital expenditure and operational expenditure incurred in both cases. But definitely, you don't go for a LoRa or an XB protocol if you don't have many, many sensors that need to be installed and relay the data to the cloud. But if you have many sensors, then this might be a very good option. You don't need to have the same type of sensors to use a LoRa protocol or an XB protocol. This system accepts the signals from all kinds of different sensors to be transmitted. So it could be water meters, it could be water levels, it could be electric conductivity, pH, ORP, and whatsoever. Another option you could explore, and you should explore, is what exactly type of protocol you are going. Also, having in mind that nothing is perfect. If you go for a GSM protocol, which would be 4G, 3G, or 2G, and mind you that 3G and 4G are probably going to be abandoned as data transmission protocols in the coming 1 or 2 years. So we're talking 5G or 2G now. These are the most trustworthy in terms of data loss. So you're looking at very, very low data loss percentage in terms of 0.1 or 0.2%. If you are going for a narrowband Internet of Things protocol, which is a relatively new protocol, then you're talking about a bit higher percentage of potential data loss, which is normally less than 5%. However, make sure that your area supports and your GSM providers support NB-IoT protocols. If you are going for the LoRa protocol, the average loss rate is pretty much high. It varies from 2 to 10%. So you need to decide if losing data is essential to you or not. However, you need to make sure to know that the more technology advances, the better the protocols become, and lately, some of the LoRa provider companies have improved their protocols, claiming rather that the data loss is reduced to a minimum of 1%, to a maximum of of 1%, thus making them very competitive to the other two solutions. Next one, Vasilis. Right. So, if we are going for telemetry with the ordinary GSM systems, please look at what's the case in Greece. If you're going for a national data provider through the national SIM cards of the Greek operators, then the cost for 10 years for an annual plan is, sorry, the annual plan for per monitoring point is about 240 euros. And this means that for 10 years, it's a huge value of almost 2,400 euros. If you go with a data plan offered through the foreign provider, I'm not going to say the country of the provider now, but individually we can tell you, then the very same data plan for 500 megabytes for 10 years in 2G, 3G, 4G, or NB-IoT is only 10 euros. So go out in the market, search very well what's available, and make up your minds. This works on roaming, but it works pretty well without extra costs. Be sure you check, otherwise you're going to be ripped off. Next one, please.
So this is my turn now. Let's see now the sensors. Sensors could be categorized into three groups. The small size probes with diameter up to 1 inch. The sensors in these probes are fixed. They are usually pressure transducers with temperature or conductivity temperature depth sensors, and there are no extra ports available to connect extra sensors. Then we have the medium size probes, which have a diameter approximately between 1 and 2 inches. Some of the sensors might be replaceable, and they usually can host up to 4 ports. Finally, we have the large sensors with diameters higher than 2 inches. They also have some replaceable sensors, and they can accommodate usually up to 6 ports. Let's see some hints regarding the pressure range options that we have. Sometimes the pressure ranges that we have for the pressure transducers is different for the vented and the non-vented cables, and this is very critical. Also, there is a great variability on the pressure ranges between the different factories, the different manufacturers, as you can see in this table below. There is also different resolution and accuracy based on the different signal protocols. We have, let's say, significant difference between the analog and the digital signals, and also the manufacturing materials and the range demonstrates different resolution and accuracies. Please have in mind that some probes have different maximum pressure ratings for the different sensors. So let's say we could have a pressure range of 100 meter for the groundwater level sensor, but only 50 meters for an ammonium, let's say, concentration sensor. And a very, very big rule. The pressure sensor is always fixed in the probe and not replaceable. So let's see now the purchase cost. Make the most from your budget by conducting a broad and detailed market research and take advantage of the different solutions found on the market. This is very, very critical. You have to get all the alternatives. There are several alternative alternatives out there, and don't rely only to what the sellers give you. Do your own research. This will save money, finally. So, some hints more. A CTD costs, the CTD cost, let's say, ranges between about 2,000 euros without any cables to more than 50,000 euros for a large probe equipped with 5 sensors, not probes as written here. So be careful not to add sensors that you don't need. You have to specify your monitoring targets and then come with the requirements that your probes should have. Also, you have to keep in mind that the sensors do not last for a whole life. They have some limited period of life, and it is critical to mention that they have a limited period of stability. Okay, the sensor may give data, but it might have lost its stability. So plan to buy and install immediately. Don't let the sensor stand somewhere in your office. Do it now and take the data now. Other hints. You can see in these photos below some interfaces, some devices that help you to communicate with your probes. You shouldn't neglect the cost of these interfaces. They could cost several hundred euros, up to 700 or 800 euros. Also, it is very critical to mention that some of the manufacturers are charging for the software that is being used for the communication setup and management of the probes. You shouldn't consider that, okay, I buy the probe, so the software is free. This is the most usual, but there are several, let's say, cases for which you have to pay extra money for the software. Cables, a big issue. Cables connecting the sensor with the logger are very expensive sometimes, especially the varied ones, which can cost more than 10 euros per meter. So don't spend your money by, let's say, ordering a cable without having a clear view of how long it should be. You should choose the cables very wisely. Now, as we said before, we have to perform the compensation for the PT sensors. If there is no, let's say, meteorological station around there, or you don't have such kind of sensor, you have to consider to include in your budget buying a barometric pressure sensor. Such a sensor could cost, let's say, 700 euros. It's a considerable cost. Okay. Andreas.
I was about to say that we're running out of time, so I'll be pretty quick. Installation. You need some technical expertise and experience. It's not always so straightforward, so if you don't know how to do it, and you cannot read and learn how to do it, better pay for it. Otherwise, you run the risk of ruining your capital expense for buying the sensors. The installation costs are sometimes very high, depending on the company. That you will ask to come and install them for you. Some works can be made by you, For instance, the sensors calibration. Sensors calibration in this type of equipment is straightforward as long as you read the manual, practice at the lab conditions, and then you go out and do it. The cost of the accommodation of the staff of the company is sometimes not covered in the standard quote they will give you, so be prepared that this may come on top. So overall, if you don't know what to do and how to do it, go to an expert. It's not a tremendously difficult job, but you need to follow specific steps. Vasilis, next one, please. Right, and then you have the maintenance, the operational cost. Don't disregard this. Don't disregard it because I need to stay here because they don't see me. Okay, because it can be very big. And if you haven't taken account of it, you might ruin the entire operation. So the operation typical maintenance usually does not require special skills, but it requires money. You need to have budget for it. You need to balance the expenses for the development of the sensors network and the maintenance and operation expenses. Big networks are easy to establish, but very difficult to operate because you need specific protocols, a lot of time, and a lot of budget. Keeping a maintenance log. You need always to keep a detailed log of when you need to service and calibrate a sensor, what you did, how you did it, what are the indications, and of course, mark a date that you will need to change the sensor because it has reached its life cycle. Do this provisionally in shorter time frames than the originally prescribed by the manufacturer, because this is a safer option. And normally, what the manufacturer gives you as a standard is way exceeding the practical lifetime for the batteries, for the drifting, for the stability period, simply because all of the measurements are done in ideal conditions of lab, which is far from being the real case in the field. What else? The environment in which a sensor is installed constitutes a critical factor for maintenance frequency. It's different to have a sensor, as we'll see in the next session, in fresh water or in a saline but not hostile environment, than have a sensor in a very hostile, very corrosive environment. Then the life period of the sensor goes down the drain. Nothing stands. As you are going to see, this is completely different story. Check the options for data transmission and storage depending on your available infrastructure, which relates to the sensor and the know-how on how to develop the database. If you are an expert or you have an expert in your team, then go for a customized database and data handling protocol. If you are not an expert or you don't have an expert in your team, then you need to be prepared to pay for a scheme or a ready-made software that will handle your data and process it through a nicely developed interface that is offered by a company, but it costs money. Last but not least, the fancy web-based interfaces are very handy. They're fantastic. They give you a bulletproof analysis and data handling of the data, but normally they come at a cost which sometimes can be very high. Next one, please, Vasilis. We're done. Excellent.
Yes, yes,
So,
yes, we've done.
Let's run because we only have 20 minutes for the final part. If you'd like to start it, then what you see so far is that we're moving from theoretical to more and more practical. And this last session is the most practical we want to offer to you, because it's the experience out of what we've done in medicine. Some are ideal, some were not so ideal, but it's the practical outcome. So, Vasilis.
Okay, so we have 5 case study areas. We have 5 test sites in which we have installed in total 11 probes. We will see one by one the groundwater monitoring, the sensor-based groundwater monitoring networks developed. So I would like to invite Fadwa Hamzawi in order to give us the presentation for Bufisha pilot site.
Yeah, advice coming. So you can come here. What's the table? Vasilis, can you go to the previous slide? Fadwa, you have to stay here so that they can see you.
Okay.
The camera is there. Okay, so now they can see you. Yeah. Vasilis, is there any previous slide?
No, this is the first slide.
Okay.
No.
The previous, Vasilis, please.
The previous. This slide.
Yeah. Thank you very much. I am very happy to be here with you. If you permit, before to start, I would take this opportunity to thank all for you to be here, our partner in the Mid-Side project, and an immense thank to Professor Dolores and Professor Gabriela and all the staff for this perfect organization. So thank you very much. I pass now to present our pilot site in Mid-Sal project. It's located in Tunisia. Tunisia is a country located in the north of Africa. It's characterized by semi-arid climate and unfortunately by water scarcity, like many regions and many countries in the world. So to preserve and to protect this resource, we must give and accordate big importance for this resource. In Mid-Sal project,
next one, Vasilis.
Voilà. So in Mid-Sal project, we choose to study the salinization phenomena, the Bufisha aquifer. Why Bufisha aquifer? Because Bufisha aquifer suffers from many problems concerning the quality and the quantity. And Bufisha aquifer is considered the main source of water in all the region of Bufisha and the governorate of Susa. So Bufisha aquifer is located in the eastern center of Tunisia. It's bordered by the Mediterranean Sea in the east and the range of mountains in the west and the Setra in the south. So Bufisha aquifer covered over 130 kilometers square, and it's characterized by an average annual precipitation of 400 millimeters. So Bufisha aquifer, as you say, is the main source of water in the region. It's exploited essentially to satisfy the agriculture activity. So the main activity, the main economic activity in the Bufisha is the agriculture. In the last decades, the excessive use of fertilizer in the Bufisha aquifer lead to the contamination of groundwater by the nitrate. We enregistrate very high concentration of nitrate in some wells in Bufisha aquifer and also make groundwater quality degradation. Also, since 2015, the abstraction and the exploitation of the Bufisha aquifer become more higher than the resource available in this aquifer. The results, a continuous increase of salinity and a continuous decrease of piezometry. So to preserve this resource and to protect this resource, besides the seasonal monitoring, we have installed the sensor to monitoring continually some parameters in the Bufisha groundwater aquifer. So the installation of the sensor is based into some criteria, such as the location in representative land use setup, the distance from the sea, and in key places to can control the piezometric level for our aquifer. Also, the security is the main criteria to choose the well where we will install the sensor. So the two wells chosen, which will operated by the Regional Commissariat for Agriculture Development to ensure efficient cooperation with this commissariat. Also, the reduced possibility for the theft or damage, sufficient diameter for probe installation, and a good quality of GSM signal. So, two wells were chosen to install the two sensors. The first well is named Ahmed Shibani with depth equal to 17 meters, and the other well is named Bekes Benadi with depth equal to 30 meters. These two wells are private and used essentially to satisfy the agricultural needs. Okay, the other. Okay, so the two sensors were installed in the same day in both wells, 29 July 2020, with Ali Ahmed Shibani. Donc, the sensors were installed under the depth 2 meters and near the sea to help us to control the phenomena of seawater intrusion. And the other well, the gas under the depth 6 meters, and many parameters were measured in situ. Thank you. After. So this table illustrated the measured parameters taken the day of installation of the two sensors. As you will say, the conductivity, the pH, the ORP parameter, and the temperature. Okay. So here are some before. So here, some photo taken with some member of the Tunisian team the day of installation of the sensor in the two wells, and in presence of the supplier of the sensor to answer the good functioning of these two sensors. Okay, thank you.
Thank you very much, Fadwa.
Thank you, Fadwa. Now it's my turn. Let's go to Rodo pilot site. We have an porous aquifer there. Yes.
We have a big stake to win. The rest,
yes,
in no more than 15 minutes, just to consume 10 minutes of lunch. Okay.
So forest run, something like this. Okay. These aquifers serve the agricultural needs, the irrigation needs of the area. We have mainly 3 different groundwater salinization processes, including seawater intrusion, geogenic factors, and also we have some paleo waters, trap saline lenses. Okay, so you can see with this yellow line the estimate that we have on the end, let's say, of the saline area. We were 2 days there, recorded several wells. We took data. We checked the signal. We contacted the owners, and we prefer the most, let's say, collaborative ones. So we choose these 3 groundwater monitoring wells. They are all agricultural. Okay, they are all private. We had some prior data from them, which were very useful. We also performed this depth profiling, easy depth profiling that I was mentioning many times in my previous slides. So we have 3 different let's say, cases of groundwater salinization. We don't have the time to get into much detail. Okay, we used 3 CTD probes. Only the one of them was telemetric. We have gathered already 2 years of data that we demonstrated to you in our first presentation. Okay, there's a video. I will land it very quickly in order to show to you how we were able to. The video is not playing. In any case, we don't have the time to play it. It does play. We took off all the pump and all the pipes. Okay, and then we attached this smaller pipe, and we reinserted everything into the groundwater well. Okay, now let's move to Salento. I would like to invite Gabriela Balaco.
3 minutes.
2.
2 minutes to midnight.
So the Salento aquifer is located at the northeastern edge of Italy and extends for about 308 square kilometers. So it's really a big aquifer. It's a carbonate aquifer, and the groundwater circulates in free condition. But considering the presence of carbonate platforms sometimes below the water level, or the presence of low permeability carbonate rock thickness, we have in contemporary also confined conditions and confined conditions, and also superficial aquifer, but with a low potential in general. We can conclude about the limit of the Salento aquifer that normally in the past we had the idea that the boundary of the Salento aquifer was the limit of the Salento Peninsula. It's not really true. The last findings led to conclude that the limits of the Salento aquifer coincide with the Salento province. And now we have the idea that the faults have an important role on the groundwater recharge and on the groundwater hydrodynamics. So the idea is Salento is a regional aquifer, but is constituted by many compartments inside. So it's necessary to analyze every part of the aquifer, considering the role enrolled by the faults. The site aquifer is the Italian pilot site, and about that, the monitoring net selected for the project include some of the historical monitoring wells of the Apulia region. We unfortunately we needed to use only a part of that because some of these wells were subjected to vandalism events or are subject to clogging. But one of these, in particular, one of these wells has been selected to monitor in continuum, and this wells is located next. Yeah, it's located in the middle. Is in Galatina, and this selection is based on several parameters in several reasons. The stratigraphy, the position, the main characteristics of the well, and overall the availability of the electrical conductivity logs for about 35 years. And about that, we have decided to install a groundwater level at about 5 meters below the water sea level, and two multiparametric sensors. One located at the top of the interface, about far from the water sea level, 50 meters above, and another one at the end, at the bottom of the transition zone, at about 115 meters below the water sea level. Unfortunately, we had many problems with these last sensors, considering the inhospitable habitat for the sensors, and after a few months, Alessandro had the possibility to verify that the signal was probably disturbed by many factors, and during a maintenance operation, we have the possibility to check that the sensors was corroded, was subjected to a high salinity of the water. Probably the last one is better. Vasilis, next. No, before. Okay, thank you. Yeah. Considering the fact that the salinity evaluated at the bottom of the transition zone was really high. We have changed and we replaced this sensor 3 times, but at the last we have decided to remove the sensor because really the habitat was really inhospitable. So I think this is the major aspect.
Thank you, Gabriella.
Let's move now to Samos. I will present Samos. Again, we have complex geologic and hydrological condition. So, we have easy ranges between 500 and 2,500 microsiemens per centimeter, with an average value of about 1,300 microsiemens per centimeter. So let's see some key information. The selected well is marked here with the blue symbol. Okay, it is within an area of high archaeological interest, and it demonstrated easy values between 1,800 and 2,700 values. Colleagues from Germany had some historical data, and they chose a low profile installation there. So this is the well. It is a public well. It is not operating. It is very close to the sea. The sensor was installed about 1.5 years ago in a pretty shallow depth. It is a telemetric sensor. Okay, and now let's move to the last one case study,
which will be presented by the very team that did the installations.
So I have 1 second.
Something like this, Cüneyt.
Yeah, Tarsus pilot site is in Turkey. We installed 2 sensors there. The study area is 240 square kilometers. The aquifer is basically deltaic aquifer, quaternary recent sedimentation, and its thickness range from 30 meters in the northwest to 500, more than 500 meters in the southeast corner, which is near the sea. There are lots of wells in the region. We did a 2-month survey to choose the sites that will be used for monitoring. You can go to the next slide, Vasilis. Vasilis.
You can change it.
Really? Pictures the same, yeah. Yeah, we did also some profiling before we install the sensors. These are the 2 final wells that we installed the sensors. The first one called TAR MBW1 is 30 meters deep, and we tried to install the sensor in the high-salinity portion of the well. And TAR MW has a strange profile. It starts as saline, but when you go deeper, it has a freshwater blob. Vasilis, next slide. So groundwater ground level elevation is very low in this coastal region. Both wells are private, not in use for any purposes. One well is, as I said before, 30 meters deep. The other one is close to 100 meters, but below the 50 meters, the diameter of the well narrows, so you can put the sensor in below that depth. Yes, next slide. We installed both sensors on June 10th, 2020, but we had lots of problems, of course, regarding GSM signals, data transmission. We spent more than 1 month after the installation to correct these problems. What else? Yeah, we have both Aquatrol 500 sensors in both wells. They measure electrical conductivity, temperature, pH, EH, in terms of ORP. Without oxygen, we are not measuring right now because it's 0 basically all the time. So we opt to not to measure it to save battery time because it consumes a lot of battery. So we increase the life of the battery a little bit. This in both wells we have rented cables. Basically, there are holes in it, so it can compensate for the barometric pressure at the surface. We use 3G technology to transmit data, but it's in automatic mode. It can switch to 4G also if it requires. Then another one was this. Yeah, this is the setup of the wells. 30 meters, our sensor is minus 22 point something. The other ones at 26.044 meters below the surface. The other one. Yeah, this is the well. We installed the sensor to protect. Can you play the video, Vasilis?
Yes, yes.
To protect the sensors from theft or other vandalism, we had to put a, how do you call it? Yes, this one.
The protective well casing.
Yeah, well casing. Not casing.
Is it protective casing?
Yeah, okay. Our purpose was to make well less visible from the outside, but due to transmission problems, we had to add an antenna above this level. So it's like 1.7 meters high now.
Hmm.
And then in the process, you know, you will try to solve the problems. There are lots of problems. We somehow managed to solve them, and just we are now doing some regular calibrations, changing sensors and maintenance. Thank you.